So today we are looking at the development logs for basically a multi-million-dollar automated AI financial trading engine.
Right, which is fascinating on its own. But the kicker is that it was intentionally built without a single drop of intelligence.
Yeah, exactly. I mean, we are doing a deep dive today into a primary source document. It's a development journal specifically dated May 14th, 2026.
And this document details the exact moment that a highly complex system, which they call OpsHub DipFire X, successfully completed its Phase 1 infrastructure.
Right. And the reason I think this document is so incredibly fascinating for you listening today is that it's essentially a masterclass in how not to build a complex system into a total catastrophic failure.
It really is a striking document. I mean, it fundamentally rejects the way most ambitious projects are built today.
Yeah, totally.
Because the stated goal for OpsHub DipFire X is to be this, institutional-grade dip-buying intelligence engine.
Right, which sounds massive.
Oh, it is. It's supposed to ingest massive amounts of market data, run these incredibly heavy quantitative analyses to detect pricing anomalies or liquidity sweeps, and then execute highly sophisticated trading strategies.
But the wild part is this entire journal covers a massive developmental sprint where the engineers and their AI code builders, they explicitly refuse to write a single algorithmic trading rule.
Not at all. Zero.
They built the entire factory, right? They poured the concrete, routed the electrical grid, established the supply chains, but they refused to put an actual product on the assembly line.
Yeah, which is so counterintuitive to how we usually work.
Right. So I really want to set the scene for you listening right now, because whether you're, I don't know, a software architect managing a massive code base, or a quantitative analyst trying to get your models into production, or honestly, even just an entrepreneur trying to scale a complex business process.
Yeah, it applies to almost anything complex.
Exactly. This development journal provides an absolute blueprint for survival. The mission of this deep dive is to really unpack this specific milestone.
To figure out why holding back, why aggressively gatekeeping the quote-unquote cool features is actually the secret to deploying institutional-grade software.
Yeah. And I think the broader context here is just, well, the culture of modern deployment, right?
Oh, absolutely.
Right.
I mean, we live in an era where development frameworks and AI coding assistants, they allow us to generate massive amounts of logic incredibly fast.
Almost too fast sometimes.
Right. The temptation is always to spin up a repository, connect a market data API, write a quick moving average crossover strategy, and just hit run.
Yeah, and that works perfectly fine for like a weekend project.
Sure, yeah.
Okay.
But when you are building an intelligence engine that needs to run autonomously, handle weird edge cases, and manage actual capital, that rapid prototyping mindset is just fatal.
It's a disaster waiting to happen.
Exactly. So this document is a study in rigorous, almost paranoid, delayed gratification.
Paranoid is the perfect word for it. Which brings us to the core philosophy driving this entire build.
The anti-monolith approach.
Right. The project leads explicitly state in the executive summary and the critical engineering decisions section that they completely rejected a monolithic architecture.
They didn't try to build the data ingestion, the AI processing, and the execution routing all at the exact same time.
No, they locked themselves into a layered build sequence. Phase 1 was strictly defined as infrastructure plus plumbing.
And then phase 1.5 was credential integration plus verification. There's a very hard line drawn there.
But I look at this and I have to ask, I mean, in the quantitative finance world, time is literally money, right? Market conditions change rapidly. Alpha decays.
Oh yeah, every second counts.
So if your goal is to capture market dips, spending weeks just building out logging frameworks and configuration routing, well, it feels like premature optimization.
That feels like a waste of time.
Right. It's like deciding to build a massive skyscraper, and the monolithic approach is trying to pour the concrete, install the elevators, and hang the penthouse drywall all on the same Tuesday. It's chaos.
It is chaos, yes.
But still, why not build a minimum viable product that actually executes a trade and then refactor the plumbing later?
Well, because in complex systems, especially automated financial systems, that refactor later phase, it never actually happens.
Right, until it's too late.
Exactly. It never happens until after a catastrophic failure forces it to happen. And the text explicitly answers your question by listing the specific failures this phased approach prevented.
They didn't just guess that a monolith would fail.
No, they engineered phase 1 to preempt very specific failure modes. The document lists silent failures, dependency chaos, debugging overload, YAML instability, scheduler corruption, and alert routing failures.
Okay, let's actually tear into that list for a second because those aren't just, generic tech buzzwords. Those are highly specific architectural
They
nightmares.
really are.
I want to start with silent failures because a system crashing and burning is bad, obviously, but a system failing silently in an automated trading environment, that is how you bankrupt a fund.
Precisely. If you build a monolithic system where your network requests, your data parsing, and your trading logic are all deeply coupled together, errors just get swallowed.
Give me an example of how that actually happens.
Okay, let's say Polygon, which is the market data provider they use. Let's say it sends a malformed JSON payload for a specific stock ticker.
So, like, the data is just formatted wrong or corrupted somehow?
Right. If your infrastructure isn't strictly isolated and independently verified, the data ingestion function might just throw an unhandled exception.
Okay.
And that exception gets caught by a generic error handler in the main trading loop. So the system doesn't crash, it stays alive.
But it stops updating the price for that specific asset.
Yes, exactly. And because it's still running, the trading logic assumes the price is just perfectly flat.
Oh, wow. So it might trigger a massive buy order based on data that's an hour old?
And you wouldn't even know until you looked at the reconciliation report the next day and realized you bought the top of a peak before a crash.
That is terrifying.
A loud failure takes your system offline, which is safe. A silent failure actively destroys capital while telling you everything is totally fine.
Right. So by building only the infrastructure first, the logging, the error catching, the state management, they can pump dummy data through the pipes to test it.
Exactly. They can intentionally send malformed packets and ensure that the system screams loudly and predictably. They are calibrating the alarms before they bring the actual vault contents inside.
That plays directly into the next item on their prevention list, which is dependency chaos.
Oh, a classic.
We're looking at a Python environment here, specifically Python 3.1.199, which the journal notes was completely verified. Anyone who has deployed Python in a production environment knows that dependency resolution is essentially a dark art.
It really is the Achilles heel of the whole ecosystem,
Yeah.
especially when you start mixing data science libraries with asynchronous networking libraries.
Right. You've got pandas and NumPy, which rely on underlying C extensions.
And then you have Python Telegram bot and the Polygon API client, which are heavily reliant on asynchronous event loops.
So if you try to build the intelligence and the infrastructure simultaneously, you might find that the specific version of an AI library you want requires a networking library that completely breaks your database driver.
And when you hit that kind of conflict in a monolithic build, your momentum stops completely.
Right, you just hit a wall.
You have engineers trying to debug a complex quantitative trading algorithm, and suddenly they're spending 3 days fighting with the Python package manager because some random transitive dependency got updated.
Yeah, I've been there. It is the worst. So by isolating phase one, they establish a frozen verified baseline.
Exactly. They install the heavy computational libraries, the database drivers, the asynchronous communication tools, and they prove that this specific matrix of versions compiles and runs seamlessly on their target operating system.
And once that's locked in, the intelligence layer that gets built in phase two has a guaranteed stable environment to inhabit.
Right. It's establishing the laws of physics for the application before you start building things inside of it.
Okay, I want to jump to scheduler corruption and alert routing failures because I think this really highlights the danger of mixing CPU-bound tasks with IO-bound tasks, which is exactly what DipFire X will eventually have to do.
That's a really great point of analysis. Modern Python relies heavily on asyncio for things like pulling data from an API or sending a message to Telegram.
And those are IO-bound tasks, right?
Yes, exactly.
Hmm.
The system spends most of its time just waiting around for a network response.
But the intelligence engine, the part that calculates relative strength index, or VWAP, or runs Bollinger Band analysis across thousands of data points, that is heavily CPU-bound.
Right. It requires intense processor time. And if you don't properly architect your concurrency model, a heavy CPU-bound calculation will totally block the asynchronous event loop.
So the system is crunching the numbers to find a dip. But because the numbers take, say, a full second to calculate, the system physically cannot process the incoming WebSocket message that says the price just dropped even further.
Or worse, it calculates that a perfect dip has occurred, it fires the trigger to buy, but the alert routing mechanism is blocked by another indicator calculation.
So the opportunity just passes by.
Yes, this is scheduler corruption. The heartbeat of the system starts skipping beats because the brain is thinking too hard.
That is such a good way to put it. The brain is thinking too hard.
So by building the alerting mechanisms, the logging, and the scheduling loops in Phase 1, completely devoid of any heavy math, they can test the absolute latency of the event loop.
They prove that the system can route messages perfectly under load, entirely unencumbered by logic.
And then, when they do introduce the heavy math in Phase 2, if the scheduler starts dropping tasks, they know exactly what caused it.
Right, they don't have to guess if their networking code is bad or if their math is too heavy. They already proved the networking code is flawless.
Exactly. It drastically reduces the debugging search space,
Yeah.
which is exactly why debugging overload is listed as one of the primary failures they avoided.
Because in a complex system, the time it takes to identify a bug is often, what, an order of magnitude larger than the time it takes to actually fix it?
Oh, easily. Finding the bug is 90% of the work.
Okay, let's talk about the actual anatomy of this foundation they built. The journal outlines a highly specific modular architecture that was generated by their AI co-builder, Claude Code.
Right, they laid out a very clear directory structure.
Yeah, they have config, data, logs, tests, SRC, agents, engine, indicators, alerts, and storage. When I look at this structure, it's clear they're utilizing a very strict separation of concerns.
Absolutely.
But what really strikes me is that they are building out empty directories for agents and indicators. I mean, the whole point of Phase 1 is that the intelligence doesn't exist yet. So they're essentially committing empty modules to the repository. In a lot of agile development environments, committing empty architecture is really frowned upon as dead code or over-engineering. Why is it a feature rather than a bug in this specific journal?
Well, it comes down to interface design and defining the boundaries of the system before the implementation even exists.
Okay, unpack that a bit.
In software architecture, especially when you are collaborating with AI code generation tools like Claude, context is literally everything. Creating the indicators directory and likely putting an empty base class or an interface definition inside it, it establishes a contract.
Ah, I see. It tells the rest of the system, like, I don't know what the specific indicator will be, but when I eventually ask for one, it will live here and it will respond to these specific function calls.
Exactly. It's all about establishing routing and dependency injection patterns. If the engine module needs to loop through all active indicators, you can write the logic for that loop right now in Phase 1.
Even though there are no indicators.
Right. You write the loop to point at the indicators directory and execute whatever it finds there. You can test that the engine successfully iterates over the directory, even if it's iterating over a bunch of dummy test files.
So you are verifying the connective tissue.
Yes. When Phase 2 begins, the AI or the human engineer doesn't have to figure out how to integrate a new MANQD indicator. They just drop the logic into the predefined slot, and the engine automatically picks it up.
They are building the sockets, so Phase 2 is just plugging in the appliances.
That's a perfect analogy.
And looking at the specific libraries they verified in this Python environment, you can see how deep this foundational thinking really goes. We mentioned pandas and NumPy for the eventual data crunching, but they also explicitly list Squalchemy, PyTest, DotMov, and PM.
Yeah, let's dig into Squalchemy, because the text makes a really strong point about establishing persistence in diagnostics.
Right. Squalchemy is an object relational mapper, an ORM, and it's used here to interface with and support database structure. But why is a database considered part of the plumbing Phase 1 rather than the intelligence Phase 2? I mean, a quantitative model doesn't necessarily need a database to calculate a moving average.
A quantitative model in isolation doesn't, no.
Right.
But an institutional-grade operational platform absolutely does.
Because of system state.
Exactly. This goes back to the concept of system state. When a trading engine makes a decision, it's not just a mathematical calculation in the moment. It involves context.
Like what?
Like, what is the current portfolio allocation? How many trades have we executed today? What was the exact parameter state of the regime engine when this buy signal fired?
Right. So if the system loses power or if a cloud instance reboots and you are holding active positions in the market, your system needs to wake up and instantly know exactly what it owns and why it owns it.
That is persistence.
Yeah.
If you build your intelligence engine using entirely in-memory data structures, just keeping variables in RAM, a simple restart creates total amnesia.
Which is terrifying with real money.
Totally. So setting up Squalchemy and the Squalite database in Phase 1 means they've constructed an ACID-compliant memory bank.
ACD meaning atomicity, consistency, isolation, durability.
Right.
And Squalite is a really fascinating choice here. It's a serverless database engine. It writes directly to a file on the local disk. They didn't spin up a massive PostgreSQL cluster. They chose a highly reliable embedded database.
Which aligns perfectly with the philosophy of a modular, self-contained intelligence engine. It minimizes external networking dependencies for core state management.
So by verifying the Squalchemy ORM now, they ensure that when Phase 2 starts generating complex trade objects or scoring metrics, the capability to permanently log those objects to disk without blocking the main execution thread is already tested and proven.
Exactly. The intelligence just hands the data to the persistence layer and moves on. It doesn't have to worry about how it gets saved.
And speaking of configuration and state, let's look at DOTNV and PYAML. The journal mentions preventing YAML instability. YAML is incredibly common for configuration files, right? For setting up parameters, defining environment variables, but it is notoriously unforgiving.
It relies on strict indentation. A single tab, instead of spaces, or an extra space at the end of a line, can render the entire configuration file completely unparsable.
So if you have a massive application and a developer tweaks a risk parameter in a YAML file and accidentally introduces a formatting error,
The application attempts to read its settings on startup, fails to parse the file, and hard crashes.
oh man. And if your configuration management is deeply intertwined with your application logic, you might spend hours trying to figure out why the database connection failed, only to realize the database connection string in the YAML file was indented by 3 spaces instead of 2.
Yes, which is maddening. By verifying the PYAML and DOTNV loaders in Phase 1, they are proving that the system can reliably read its own DNA.
They build in the error handling for malformed configs before the configs actually contain critical API keys or trading parameters.
Exactly. It's all about preemptive stability.
Okay, so the directory structure is perfect. The dependencies are locked, the persistence layer is active, the configuration loaders are hardened. But having a beautiful architecture on your local machine is meaningless if it can't survive deployment.
True.
And this is where the journal shifts gears entirely. It moves from what they built to how they attacked what they built. Let's look at the infrastructure validation pipeline executed section.
This part is great.
They ran an 11-stage validation sequence. We are talking about a full CI/CD, continuous integration, and continuous deployment mentality applied at the very first breath of the project.
It is a remarkable level of rigor, 11 distinct stages of validation just for the infrastructure layer.
And the document highlights some very specific protections that were verified during this pipeline. The first one is UTF-8 hardening, specifically implemented to fix Windows console and coding issues.
Yeah, that one is so specific.
I have to admit, when I first read this, it felt a little granular, like a state-of-the-art AI trading bot highlighting a text encoding fix as a major accomplishment. But when you consider the environment this will run in, it actually exposes a massive vulnerability in amateur builds.
It's the kind of bug that you don't believe can actually take down $1 million system until it happens to you.
Okay, break that down for me.
To understand why it's critical, you have to understand observability. When a complex automated system is running in the cloud, you don't have a user interface. You don't have a visual dashboard right away. The only way you know what the system is doing or why it made a decision is by reading the telemetry.
The logs it spits out to the console or writes to a file.
Right. It's logging timestamps, price data, error states, network responses. And that data is coming from the wild. It's pulling from Polygon's global API. It's receiving messages from Telegram users who might have their keyboards set to different languages.
Oh, I see. It might pull a news headline about a foreign company with specialized characters in its name.
Exactly. And historically, the default console on Windows, or even improperly configured Linux environments, it does not default to UTF-8 encoding. It might expect basic ASCII.
Because of what happens?
Well, imagine the system is running perfectly. The massive intelligence engine detects a dip on a foreign asset. It formulates a brilliant trade. And as it executes the trade, it attempts to write a simple log message, like executing buy on asset, and includes the asset's name.
But the asset name contains a unique Unicode character.
Yes. The Python logging module attempts to push that character to a console that doesn't understand UTF-8.
And the console throws a Unicode encode error.
And because it's an unhandled exception at the core logging level, the entire Python process just halts. The trade doesn't go through, the system dies.
Oh my God. Not because the intelligence was wrong, not because the network failed, but because it didn't know how to print a letter to a screen that no human was even looking at.
It is the ultimate silent killer. By making UTF-8 hardening a verified checkpoint in Phase 1, they are ensuring that their observability pipeline is bulletproof.
They are guaranteeing that no matter what garbage data the internet throws at their system, the system will never crash, simply trying to log it.
Right. It separates the presentation layer from the execution layer perfectly.
That level of paranoia is exactly what institutional systems require, which leads directly into the next protection they verified, which is perhaps the most crucial safety mechanism in the entire document, the DRI-run protection.
Yes, the safety switch.
The journal states, safe mode protections verified. Important. The system temporarily flipped out of DRI-run mode for a single Telegram verification test, then safely restored DRI-run equals true automatically afterward. Let's unpack the mechanics of a dry run in this context and why automating the state mutation is such a big deal.
In any system that executes real-world actions, whether it's firing a thruster on a satellite, modifying a production database, or sending a buy order to a financial exchange, you absolutely must have a global safety switch, a dry run mode. When dry run is active, the software executes every single line of logic, it makes every calculation, it logs what its decision would be, but at the very last millisecond, the actual HTTP request to the external world is intercepted and blocked.
It's the ultimate simulation layer. It allows you to run your new trading algorithm against live market data, watching its decision-making in real time without risking a single penny of actual capital.
Precisely. And in a professional environment, DRI run equals true is the default state. The system is born with the safety on. You only take the safety off when you are absolutely certain you are ready for live execution.
But the testing pipeline here did something highly complex. To verify that the Telegram alert routing actually worked, the automated test suite had to temporarily mutate the global state.
Right.
It had to flip DRI-run to false, send a real ping to the Telegram API to prove connectivity, and then flip DRI-run back to true. Why is the document making such a huge point that this was done automatically by the pipeline? Why not just have a developer manually test it?
Because relying on human memory to manage global safety states is an unacceptable risk. Let's look at the manual process. A developer wants to test Telegram. They open the .env file. They manually change DRI-run equals true to DRI-run equals false.
Okay.
They run the script. Their phone buzzes with a Telegram message. Test successful. They get up to grab a coffee, they get pulled into a meeting, and they push their code to the repository.
With the safety left off.
Exactly. The next day, the quantitative team merges a highly experimental, unverified momentum algorithm into the main branch and runs it, assuming the system is in safe mode.
Oh, no.
But it isn't. The system immediately starts buying assets with real money based on broken logic.
It's a catastrophic deployment failure caused by a single forgotten keystroke.
By engineering the test suite, using the PyTest framework we discussed earlier, to programmatically manage the state, they eliminate the human element entirely.
So the test itself handles it.
Yes. The test uses a setup and teardown method. It asserts the state is true. It forcefully injects a false state into the specific localized context of the test, executes the network call, and then the teardown method mathematically guarantees the global state is reverted to true, regardless of whether the test passed or failed.
The testing pipeline is basically cleaning up its own blast radius.
Exactly.
And that concept, the system managing itself, transitions perfectly into what I think is the most futuristic, cutting-edge revelation in this entire journal.
Oh, the self-healing stuff?
Yes. This isn't just a document about static architecture. It's a document about an active, self-aware deployment process. Let's dig into the notable recovery behavior section.
This is where we see the real power of integrating AI into the infrastructure pipeline, not just as a code generation tool, but as an active agent.
Right. The journal logs a specific event during the build process. It notes that a .example path mismatch occurred. So basically, a file path was incorrect. But it's what happens next that is astonishing. The journal lists the sequence. The AI assistant, Claude Code, detected the issue. It corrected the path automatically, it regenerated the environment file successfully, and it reran the validations.
On its own.
Yes. Now, I want to play devil's advocate here because if you are a traditional software engineer, you might look at this and just laugh. You might say, wait, the AI wrote the code, the AI made a mistake with a file path, the AI caught its own mistake, and the AI fixed it. It's just spinning its wheels, it's inefficient. If I wrote it, I would have just gotten the path right the first time.
Yeah, that's a common reaction.
So why is this highlighted as a massive success in institutional deployment?
It's a phenomenal question. And answering it requires a real shift in how we view complex systems.
Yeah.
The old paradigm of software engineering was the pursuit of perfection. You write the perfect script and it runs perfectly every time.
Right.
But Modern cloud infrastructure, complex dependency trees, and asynchronous environments are inherently chaotic. Perfection is impossible. Entropy is the baseline.
So things are just going to break.
Always. A path mismatch might occur, not because of a quote-unquote dumb error, but because a dependency installation slightly altered a directory structure or a cross-platform OS difference between the developed machine and the deployment server caused a relative path to resolve differently.
So errors are basically just the weather. You can't prevent them, you just have to navigate them.
Exactly. And the traditional way of navigating them is extremely fragile. In a traditional CI/CD pipeline, the script runs, it hits a path mismatch, it throws a fatal exit code, and the pipeline halts.
And then a Slack message is sent to a DevOps engineer.
Right. That engineer has to drop what they are doing, read the stack trace, locate the mismatched file, manually edit the text, commit the fix, and restart the 20-minute pipeline from scratch. It is a massive drain on human capital and momentum.
But what we are seeing in this journal is the implementation of automated infrastructure resilience. The AI isn't just a static script, it's an agent with a feedback loop.
Let's actually break down the mechanics of what Claude Code had to do here. It executed a bash command to run the pipeline. The pipeline failed. The agent had to read standard error output, STRDR. It had to use natural language processing to understand the stack trace and pinpoint the root cause, which in this case was a file path.
Okay, wow.
Then it had to locate that file in its own workspace, generate a file editing command, mutate the text string to fix the relative path, save the file, and then autonomously execute the bash command to run the tests again.
It's autonomous DevOps.
It really is. And the journal highlights this because it proves the architecture they built is stable enough to allow for autonomous repair. Think about it. If they had built a monolithic system, letting an AI autonomously edit configuration files in real time during a build would be terrifying.
Oh, yeah. It might accidentally overwrite a critical piece of trading logic while trying to fix a logging path.
Exactly. But because the system is perfectly compartmentalized, the AI can safely operate within the infrastructure layer without cross-contaminating the eventual intelligence layer. The boundaries are so clear that the self-healing behavior is actually safe.
It proves that they haven't just built a robust system, they have built a system capable of adapting to its own deployment friction. The milestone isn't that code was written. The milestone is that a self-correcting deployment loop was successfully established and verified.
Absolutely perfectly said.
Okay, so let's take stock of where we are. The directory skeleton is perfect. The internal state can be saved flawlessly via SQLite. The configuration files are hardened against formatting errors. The logging system is immune to strange text characters. The safety switches turn themselves back on automatically. And the deployment engine can detect and heal its own minor injuries.
It's an impenetrable vault.
It is, but right now, it is completely isolated from the universe. A trading bot that doesn't know what the stock market is doing isn't very useful.
Right, it needs input.
Which brings us to phase 1.5. The journal calls this credential integration plus verification. I look at this as opening the system's senses.
It's the critical threshold where the internal architecture makes first contact with the external environment. And again, the discipline they show here is just remarkable.
They integrated two massive external lifelines, Telegram and Polygon. Telegram provides the system with a voice. It's how the bot will communicate with the human operators, sending alerts, status updates, and execution confirmations.
And Polygon provides the system with eyes.
Right. It's the API that will feed it the fire hose of real-time and historical market data, stock ticks, crypto prices, everything. The journal notes that they successfully validated the Telegram bot token and chat ID and successfully authenticated a delivery message. We talked a little about that with the DRYR-Woon tested.
Right, the automated state flip.
But let's focus on the Polygon integration for a second. The text states Polygon credentials successfully validated and authenticated locally through environment configuration. I really want to focus on the word locally. They authenticated the credentials, they proved they had the keys to the kingdom, but they did it locally. They didn't actually pull any market data. Why not? I mean, if you have the API key, why not just run a quick test to pull the last 5 minutes of the S&P 500 just to see it work? It would be so satisfying.
Because it violates the strict boundary of phase 1. Pulling real-time market data is not a plumbing task. It is an intelligence and memory management task.
How so? Isn't it just a simple HTTP request?
For a simple weather API, maybe. But financial market data, especially from a massive provider like Polygon, is a relentless stream. If you open a WebSocket to Polygon to listen to tick data, you aren't just making a request, you are standing in front of a fire hose. You are receiving thousands of JSON objects a second.
Oh, wow. Okay, I see. And to handle that, you need a highly optimized asynchronous queue, you need memory buffers, you need logic to handle drop packets, and you need a routing engine to distribute that data to the various indicators.
None of which exists yet. The intelligence engines haven't been built. If they open the WebSocket to Polygon right now, the data would flood the system, the memory buffers would overflow, the event loop would crash, and the entire process would die.
So by validating the credentials locally through environment configuration, what exactly are they doing?
They are simply proving that the internal plumbing can successfully read the secret API key from the hardened.env file, load it into the system memory securely, and format the authentication header correctly. They are walking up to the Polygon server, knocking on the door, holding up their ID badge, waiting for the server to say badge valid, and immediately walking away without asking for anything.
It's incredible restraint. It proves the authorization pathways are perfect without inducing any operational risk whatsoever. And the journal states that this specific phase officially upgraded DipFire X from a conceptual architecture to an operational infrastructure platform.
It ceases to be an idea and becomes a functional, connected entity. It just doesn't have a brain yet.
Which brings us to the final and perhaps most illuminating section of this deep dive. We spent all this time talking about the plumbing, the pipelines, the self-healing scripts. Now we have to confront the ghost in the shell. We have to look at what was intentionally left out.
The roadmap.
Yes. The journal includes a section titled Current DipFire X Status and explicitly lists what is not built yet. It is a roadmap for Phase 2, and the sheer density of computational intelligence on this list is absolutely staggering.
It truly reveals the massive scope of the ambition here. The infrastructure they built wasn't overkill. It was an absolute necessity to support the weight of what's coming next. Let's look at the engines they plan to build.
Right. The list includes the RSI engine, VWAP engine, email relationships, ATR engine, Bollinger Bands, volume analysis, liquidity sweep detection, regime engine, dip scoring, heartbeat escalation, and the opportunity engine.
It's huge.
For you listening, if you aren't deep into quantitative analysis, let's just contextualize just how heavy this math is. Things like RSI, which is Relative Strength Index, or EMA, Exponential Moving Averages. Those are standard indicators. They require maintaining rolling windows of historical data.
Which means constant memory allocation and deallocation as new data points arrive.
Exactly. But then you get into things like liquidity sweep detection. This implies the system needs to analyze the order book, looking for specific volume spikes that indicate large institutional players are manipulating price to grab available shares. That requires parsing massive amounts of granular tick data in real time.
And then there is the regime engine. This is the holy grail of algorithmic trading. A regime engine doesn't just look at the price of an asset, it attempts to classify the macro state of the entire market. Is the market trending up? Is it a high volatility chop? Is it a mean reverting environment?
To calculate that, the system has to process multiple assets across multiple timeframes simultaneously. It's performing complex statistical analysis, perhaps hidden Markov models or advanced clustering algorithms, just to figure out what kind of math it should be using at any given moment.
But all of that data, from the RSI to the regime engine, has to feed into the dip scoring module. The system has to weigh dozens of conflicting signals, assign a numerical probability to the trade, and make a binary decision to execute or pass.
And it has to do all of this in milliseconds concurrently without blocking the event loop that is pulling the new data in. When you lay it all out like that, it's terrifying.
Oh, completely.
It's a massive, multi-layered analytical pipeline. Every single component is a potential point of failure. Which brings me to the final reflection of the journal. I want to read this because I think it's one of the most profound statements I've ever seen in an engineering log.
Go for it.
It says, the most important achievement of this session was not intelligence itself. You have a team building an AI trading bot, and they explicitly conclude that the intelligence is not the most important part.
I will fiercely defend this conclusion. It is the absolute truth of complex systems engineering. The text lists the true achievements: stability, validation, persistence, diagnostics, communication, deployment discipline.
All the boring stuff.
Exactly. Let's do a thought experiment. Let's imagine they ignored this entire journal. They didn't do phase 1. They jumped straight to the fun stuff. They built the regime engine, the liquidity sweep detection, and the opportunity engine. The math is beautiful. The logic is flawless.
The ultimate monolith.
Exactly. They run it. The regime engine correctly identifies a major market shift. The opportunity engine calculates a massive arbitrage opportunity. The dip scoring module gives it a 99% probability of success. It is a perfect trade.
Okay, so they are about to make $1 million.
Right. The system attempts to execute. But because they didn't isolate and test the persistence layer, the SQL database lock times out under the heavy CPU load of the regime engine. The system throws an error. Because they didn't harden the UTF-8 console, the error message itself crashes the logging system. The system dies silently. Because they didn't verify the Telegram alert routing independently, the error is never broadcasted to the operators.
So the greatest trading logic in the world is completely neutralized because the plumbing couldn't handle the water pressure.
Yes, the intelligence of the system is entirely constrained by the stability of its infrastructure. The true genius of Phase 1 is recognizing that fact and submitting to the discipline of delayed gratification. They are stating unequivocally that they respect the complexity of the intelligence they are about to build so much that they refuse to subject it to a fragile environment.
You don't put a Formula One engine inside a chassis built out of balsa wood.
And you don't build a multi-time frame polygon candle analysis engine until you've proven your system can handle a .end file path mismatch without panicking. The journal states that this session established the foundation for what can eventually become a highly sophisticated institutional platform. The key word is eventually. They earned the right to build complexity by proving they could master simplicity.
So let's bring this all together. What is the grand unified takeaway from the OpsHub DipFire X Phase 1 journal? It's a masterclass in architectural restraint.
That's the perfect summary.
We've learned that to build something truly ambitious, something that won't collapse under its own weight, you have to actively fight the urge to build the monolith. You must ruthlessly separate the infrastructure from the intelligence.
You build the empty directories, you establish the data contracts, you verify the mathematical libraries and the database drivers before you ever ask them to process a single meaningful thought.
You implement paranoid validation pipelines. You harden your observability against the most mundane errors, like text encoding, because in a headless system, your logs are your only lifeline. You engineer safety switches, like the drwire run toggle that programmatically protect humans from their own forgetfulness.
And you lean into self-healing architectures. You accept that entropy is inevitable, and you build deployment loops that can detect an anomaly, fix the configuration, and re-verify the system without requiring human intervention. You build a foundation that is not just solid, but resilient.
Only then do you open the senses. You verify your external credentials, your data fire hoses, and your communication platforms locally, securely, without inducing operational risk. You create the perfect empty shell.
Because the speed of your eventual success is entirely dependent on how slowly and methodically you are willing to build your foundation.
It's the ultimate paradox of engineering, really. Slowing down to build the invisible plumbing is the only way to eventually move at lightning speed.
Absolutely.
As we wrap up this deep dive, I want to leave you, the listener, with a final thought to chew on. We just spent this entire time analyzing a document where an advanced AI co-builder, a machine intelligence capable of generating massive amounts of complex algorithmic logic, instantly, intentionally chose to hold back.
You chose to work slowly.
Yes, phase by phase, focusing on empty directories, configuration files, and background plumbing, just to ensure absolute stability. If a machine intelligence, which processes information at the speed of light, recognizes that rushing the process inevitably leads to systemic collapse, well, why do we as humans still try to rush and build our own massive projects all at once?
That is the question, isn't it?
Think about your own life, your own code base, or your own business. What monolithic project are you trying to rush right now? What skyscraper are you trying to build in a single day that desperately needs you to pause, step back, and focus solely on your Phase 1 infrastructure? Because remember, the most important achievement isn't filling the vault with gold, it's proving the vault can withstand the pressure before the gold ever arrives.